startup and economics department at IIT. So I was initially with math and stat. Now, it's a very, you might find this title as complex optimization for data sciences is quite vague, because so many things in data science. Statistics could be data science. Image processing is obviously data science. Anything to do with medicine could be data science. So it's a vague title, but essentially I'm going to tell you what are the key methods of optimization that is useful for data science. And also I want to tell you what are the differences in approach of mathematicians, between mathematicians and computer scientists, because now this subject is this subject of data science is heavily linked with CS. So it's very pertinent as what they think, and why sometimes there is a kind of friction between the two approaches, and there is a gap, and that gap is still not been fully filled, right? So let us try to see this. So Akshay, can I go to the next slide, please? Next slide. So data science, as I told you, it can mean machine learning. Statistical learning is actually the real background behind which machine learning lurks, because yeah. So here, as I told you, that there's two kinds of researchers who work in convex optimization. One is the mathematical optimizer, for whom convergence analysis is the key. That when you design an algorithm, algorithms are iterative processes. So you choose a point and see whether it is a solution of the problem. If not, then try to go to another point where the functional value actually goes down. This is a very naive methodology, if you think, but that is exactly what an optimization algorithm does. The clever part of the algorithm is how to move from a point which is not an optimizer to the point which has a lesser functional value than the previous one. Please understand that necessary conditions of optimality that you study is very useful here. That actually allows you to decide whether a point is optimal or not. For example, you are all aware that if you have a function from Rn to Rn, you want to compute a global minimum, a local minimum minimizer, then the first thing you do is you find a point at which the gradient vanishes. And we say, okay, this is the necessary condition, and then you try to use second order conditions. But most people do not realize what is the key idea behind this necessary condition. One might say, okay, this allows me to compute the point. No, that is not the key idea. The key idea is the following, that if x naught is a local minimizer, we can prove that the gradient at that point must vanish. So if the gradient at a given point doesn't vanish, it is not a local minimizer. So it is actually a negativity certificate. That is what it guarantees. If you have a point where the gradient doesn't vanish, then it is not a local minimizer. This is the key idea. So if you really want to have, you want to find a local minimizer, you have to choose it from points where the gradient must vanish. So, for example, I give you for example, a function like, say, x minus 1 cube plus y square, a function like this. So here it will be, say, the point 1, 0 would be the only critical point, only point where the gradient vanishes, but it is not a minimizer or maximizer or anything. So that is why you need second order conditions to have additional checks. So to get a minimizer, you really have to choose from that set of points. So this is the key idea of a necessary condition. So necessary conditions are very important, actually. And that necessary conditions are good checks. So how would you check whether a point is a solution or not? You check whether the necessary condition fails or not. So then, based on that, optimizers devise rules called iterative conditions to move from iterate k to iterate k plus 1. What optimizers are interested in is moving from, as I move from one iterates to other, so I have this sequence of iterates, where do they go and hit? Does it go and hit a point? And is that point a solution? That's the question. That's what is called the convergence analysis. Computer scientists have said, no, we have to run algorithms faster. We have to complete it in fast. We have to fast go to some solution which will approximately solve the problem. That is, find given a precision level of approximation epsilon, find an x such that f of x is less than equal to the actual minimizing value f star, minimum value f star, plus that epsilon. So this comes out of this will always exist, because if you have a lower bound, the approximate minimizer will always exist. So computer scientists are more interested in devising an algorithm which will go in polynomial steps, means in reasonably less amount of time or less amount of steps, or with less amount of iterations, it will reach this point. But the whole point is that the gap what lies between convergence analysis and choosing just the so-called approximate minimizer is the following. See, approximate minimizer can be reached very fast. That is what they design. That's what they call the complexity results of optimization. When a mathematical optimizer talks about xk going to the solution x star, the iterates going to the solution x star, he doesn't talk about how much time or how much iteration it would take. But mathematically, if k is very, very large, I can be sure to a certain extent that I am quite near x star, the solution. But when I get an approximate optimizer, that there is no way I can know whether this approximate optimizer is actually very near the solution set. There's no way I can know. But what you do, there's a trade-off. You don't know that, but the trade-off is that I come to that point very fast. So that is the issue. This gap has not been filled up yet, and I do not know whether this gap can be filled up for all classes of function, but for some class or one class of Lasso problem. Recently I heard a lecture just this Monday. There is a seminar series called One World Optimization Seminar. So this which consists of a lot of optimizers around the world. So there, somebody from youngster from Cambridge was speaking about this particular issue. So this, and only one class of problems where they have been able to manage this issue, that okay, when I get an approximate optimizer, that optimizer is actually near the solution set. So this is the gap. So it's very important that when you go into data science, you need to go in understanding these two gaps. Even when you go to do research in optimization algorithms, you need to know this particular gap, because without knowing this gap, it's very difficult to really make out what you're doing. See, I have been into interview when I facing into PhD boards where people just apply genetic algorithm and say, okay, that's it, forget it, kind of thing. This is a global minimizer. So it's a rampant announcements, but these are very dangerous announcements, because I remember doing a research with Professor Kalyan Moydev, who is very famous in evolutionary algorithms, that what an evolutionary algorithm gives for a problem which can also be attacked by normal, say, standard optimization methods, the output is the same. In many cases, they are just giving KKT points. They are not even giving me they are not even somewhere near optimizers, actual optimizers, not local or global, nobody knows. So one has to be very careful about when they make this bland straight assumptions. So in optimization, one has to be conceptually very clear about what one is doing and what are the drawbacks or what are the issues that underlie that whole process. So for a mathematical optimizer, time is not really whether I'm reaching the solution finally within time. While for a computer scientist, it's different. So let's go to the next slide. Akshay, next slide. So let me take a very no, I think there's another slide before it. So the projected gradient method. So I'll talk about this and show you the two views. Okay. So what is this projected gradient method? So let us assume that f is a differentiable convex function. We'll just talk about convex functions. So it can be done for non-convex also, but let us just talk about convex function. And my job is to find the minimum of f over a convex set C. So the iterative scheme, this is a very well-known iterative scheme that xk plus 1 must be the projection on the set C of the vector xk minus lambda k grad of fxk. Xk is the kth iterate. Now I have no idea how many of you are conversant with the idea of projection, because I am possibly guessing that you know some bit of convexity. So maybe I shouldn't be doing so, but okay, take it from me.
I don't think anyone here is conversant with that idea. Maybe a few mathematicians, a few people with mathematics background, but I don't think it's, I mean, based on our experience with the past lectures, I think it's a far advanced topic.
Oh, okay. Let us assume for the moment that C is Rn. When C is Rn, the point is projected back to the same point. Okay. Projection is nothing. You have a set and then you have a point outside and you are dropping a perpendicular on the set. The point where it hits the perpendicular hits the set, that is called the projection point. And that is the nearest point of the set from the given point outside. So it might not be, it's not so apparent if I tell you in so fast what is it. It needs actually a whole class to discuss projection and its issue. So maybe 1.5 actually. So but doesn't matter. So if I take C is equal to Rn, I get the gradient descent method, which is the holy grail of machine learning, and they use probabilistic methods to solve it, and that is called the stochastic gradient descent method. So let us go to the next slide. So now the mathematician's view. So the mathematician's view is that what are the conditions that must be satisfied so that the iterate sequence finally goes and hits the solution. Though Weierstrass or Bolzano, the priest from Prague, would never know it, but whole of optimization theory is essentially the algorithms is based on Bolzano-Weierstrass theorem. So let us see what does the result say. Sorry, there is a mistake. I forgot to put the name of the book, the author. Here it will be Ruzinski, Nonlinear Optimization by Andrew A. Ruzinski, published by Princeton University Press. So sorry for that. So no, let me go to the. So what does it say? Is that okay? F is differentiable and convex, and f has a Lipschitz gradient. The gradient of the function has to be also a Lipschitz function, means satisfying this kind of property. And if x0 is a starting solution, and this particular set, so if x0 is the starting solution, means if that is not the solution, then the solution must be lurking somewhere in this set, the level set actually. This set is bound, if that set is bounded, and if I set my step length lambda that you have seen in the previous slide within 0 and 1 by L, then I can prove that the sequence that I generate xk is bounded, and every bounded sequence is a convergence sequence, a convergence subsequence. So any such convergence subsequence will go and hit a minimizer of the function f over c. So this is, so actually you see mathematicians will assume certain things which you may or may not like as engineers, but they do assume, but I don't think they, when you really apply them, you hardly check them. So there is a lot of difference between when your mathematician is implementing something on the machine and when somebody is actually writing a theorem. This assumption of Lipschitz gradient might be look too uh, difficult. Like unless f is a quadratic function, linear function, or some very complicated looking convex function, this may not be true. But though for proving that xk is bounded and every limit point is a minimizer of f over c, you need such kind of a universal condition like this Lipschitz gradient condition that is true for all xy in R, all xy in Rn, sorry, not R, all xy in Rn. The whole point is that these conditions in reality has to be checked locally. And then you can just think of convergence happening at a local level. If you start with a x naught which is very near the minimizer. Otherwise, if you want to have a global convergence, such global requirements are necessary. And this is a very stringent condition. And this happens in almost all algorithms. Take a good algorithm book, mathematical optimization algorithm book, and look at Nocedal and Wright, which engineers use it very heavily. Numerical optimization. Open Nocedal and Wright and have a look at Nocedal and Wright. This is filled with this condition, Lipschitz gradient. But in practice, why you use those algorithms? Because in reality, you have to think of it in a local sense. That if I am already near the solution, my starting point, then in a local sense, every continuously differentiable function is local Lipschitz in a certain neighborhood. So in a local sense, all these conditions will hold, and hence the convergence will be guaranteed. So that's the thing. But if you want to present the result in a global setting, you have to make global assumptions. Okay. So let us go to the computer scientist view. The next slide. Next slide, Akshay. You see, computer scientists here don't make assumptions. If you do not make Lipschitz gradient assumption, you cannot prove that when I compute the f at xk and when I get xk plus and I compute the f at xk plus 1, the value of f at xk plus 1 is strictly less than the value of f of xk because I am minimizing. So I have to keep on reducing my functional values. That is not guaranteed unless this Lipschitz gradient condition holds. It's quite dramatic actually. But computer scientists are always not bothered when they try to find some kind of an approximate solution. They're not bothered with your Lipschitz gradient or x gradient or y gradient. They're not always fully bothered with that. So sometimes they also have to bother with Lipschitz gradient, but they are not bothered that whether the function value is decreasing or not decreasing. So suppose I just want to run n iterations. So here comes a more practical point of view. For mathematician, everything sequence, n going to infinity. But for a computer scientist, your n will not go to infinity. N has to have a number. So let us see what is the output after n iterations. So if your function value is actually decreasing, then the final iteration could be n. Or in some case, they prefer an average, which is called the ergodic output, ergodic sum, that you make a vector, you sum the vectors, outputs x1, x0, x1, x2, xk, and divide by 1 by n or 1 by n plus 1 if you want here. So usually it's divided by 1 by n. It's called an ergodic average. Or if you do not know whether Lipschitz condition is guaranteed, that gradient Lipschitz condition, and so you want to just figure out, so you compute fx naught dot 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 fxn and find x hat for which the function value among all these is minimum. Maybe fx2 is the minimum. So x hat best is x2. So you take as your output. So computer scientists under different situations take different outputs. Next slide, Akshay. So let us see the difference in which computer scientists are thinking. Here it is. This is from a book by Pratik Jain of Microsoft and Purushottam Kaur of IIT Kanpur CSE. So they wrote a book on non-convex optimization for machine learning, a good one actually, and very good actually, very good book. And so Purushottam gave me a copy, and so there they did this proof. So here they not bother about Lipschitz gradient. They're telling that the gradient itself is bounded by some g, so within the set C, the gradient of fx must be bounded by some set g, say, right? So I think it shouldn't be k equal to 0. It should be k equal to 1 to n. Doesn't matter. If it is 0 to n, it should be n plus 1. Okay. So what a computer scientist wants is the following, is that they fix the step size. For a mathematician, the step size is adaptable. You can keep on changing the step size at every iteration. That lambda xk plus 1 is equal to xk minus lambda k grad of fxk, right? So that's the gradient descent method. So here they fix it up. And suppose I want to go up to n steps. Then what they prove, that for n is equal to, it will be big O, not small o, n is equal to capital O of 1 by epsilon square, that is n is some constant into 1 by epsilon square. Within that amount of step, your average of the functional values would be less than f star plus epsilon. So kind of an approximate minimal value is obtained, where f star is the infimum value or the minimum value. I assume the minimum value exists. There's a minimizer. So there's a x star. So f star is f of x, some f of x star. So this is the kind they need. So this is this O1 by epsilon square, that how many number of steps, that is the complexity value. That is the complexity of the algorithm. Number of iterations that you need actually to solve the problem. So that is what computer scientists are interested in. They are not finding one xk, they are finding all the x's and then taking the average of the functional values. If that average functional value is less than equal to f star plus epsilon, then I am done. Then I can choose any of those kind of, then it's up to me to decide what kind of iteration I want to choose. But computer scientists in most cases choose ergodic convergence. Why? Here there is no guarantee that the function value is decreasing. This doesn't guarantee that the function value is decreasing. It only says that the function itself is Lipschitz over the whole domain. It doesn't at all say whether the function value is actually decreasing from one iterate to the other. So these are called non-monotone methods. So you just cannot guarantee decrease. So if you can't guarantee decrease, then you just have to do certain things like this. And that's what computer scientists are interested in. I'm happy if I just get this. This happens with stochastic gradient descent, because this is so much of a fad now that everybody talks about it without really realizing what they do in stochastic gradient descent. That when they take, the stochasticity allows a very fast run to a point, and after that, when you come quite near the solution but not very near, your thing will slow down heavily. So computer scientists are interested in coming to that point only, but a mathematician would like to go more near to the solution. And for a mathematician, steepest descent method is not a very good choice for a classical optimizer like me, for example, because of the zigzag zigzagging of step size. So you take a step size decay, one descent direction. In the next descent direction, the step size will come down. It will be perpendicular to the previous descent direction, and this zigzagging will actually delay the convergence to the minimizer. So you will take a lot of time to go near the minimizer. And that is why for a mathematician or a classical mathematical optimizer, this is a very slow process. But for a computer scientist using the stochasticity, they know that within certain amount of steps, they will be quite near, not near, but within certain range of the minimizer, and that's okay for them. So this is exactly one of the kind of things that you see here on the screen, that they are okay if you have a scenario like this. But a mathematician might just not be okay with a scenario like this. So there is a lot of trade-off in the way which mathematicians are looking and which computer scientists are looking. I have given a part of this lecture in a university in Thailand, through online, of course. So there also this whole issue. I'm trying through building up these slides is to bring in these two difference of viewpoints. It's not just to give you some items, but to bring in the two difference of viewpoints. How some mathematicians are trying to make a balance between the two. So, okay, next slide. If there is any problem with, is this the next slide? Okay. So if there is any problem in understanding, anybody is free to stop me at any time. I understand this is very technical, and unless you are part of this optimization community from either side, this might not always be simple. So solving linear systems of equations are what we have studied in schools with 2 equations and 2 variables, maximum 3 equations, 3 variables. Then we studied through linear algebra in college, in institutes, engineering colleges, whatever. So we think that this is a kind of story that finishes in the classroom in Math 102 type courses. But it is the key story of many, many things in science and technology. In economics, for example, a lot of problem ultimately boils down to solve the system of equation Ax equal to B, where A could be an M cross N matrix and B is an element in Rm. I have not written those technical details because I am assuming that those can be understood. Now, what happens in many, many situations, so how it does it different from, how does in real applications, this solving of Ax equal to B differs from my actual linear algebra classes? It differs because then in real applications, you don't just need any solution. Possibly a system can have more than one solution, even if it is a square matrix. If the square matrix is not invertible, it can have many solutions. So if it has many solutions, I just don't want you give me one of them. No, for a particular problem, a particular type of solution might be more important. That, okay, I need a solution which has the least norm, or I need a solution which has sparse entries, means most of the entries are 0. Can I get such a solution? It has been observed that, but there is no guarantee, and nobody can say why. Largely, it has been observed, if you now choose among the solutions of Ax equal to B, the one which minimizes the L1 norm of the solution, the vector x, that leads in most situations to a sparse solution. So norm of x1 is not the usual Euclidean norm. So if x is a vector given by the components x1, x2, xn in Rn, then the norm of x of one norm or L1 norm is defined as absolute value of x1, because they are real numbers, plus absolute value of x2 plus dot 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 absolute value of xn. It is the sum of the absolute values of x. It is exactly the taxi cab norm that you learn about, or the Manhattan norm. So you need to minimize that norm over Ax equal to B. Of course, you can say that okay, there's a difficulty. For convex optimizer might say, okay, there's a difficulty because you have AX, this norm X1 need not be differentiable at everywhere. Others say, okay, I can forget that difficulty because I can write this problem as a linear programming problem. Because I can write this as minimize t, I introduce a new variable subject to norm x1 less than equal to t and ax equal to b. Now norm x can be written as summation absolute values of xi's. So basically xi lying between t and minus t. So there are, so for each of the xi's there are n, so there will be 2n constants that you add plus whatever constants you have. So some people will say, okay, this is too bad that you have to add linear programming, but if n is very large, the number of constants will become very large. So there is a lot of issues in tackling this problem. These are called basis pursuit problems, which, and these kind of problems are quite common in compressed sensing. So how does one approach such problems? Let's get into that. So next slide. One very important way of addressing such a problem is the Lasso formulation. Then this is used pretty well in machine learning. This is a kind of balance between the error that one can have when you fit a curve for a given set of points, kind of regression, and overfitting the curve, right? So there is a kind of balance that has been done by these kind of lasso problems. Lasso means a rope, actually, lasso rope. So what you do, that instead of, you always know that if Ax equal to B has a solution X, then X is the minimizer of the problem, minimize norm Ax minus B whole square. And this is a unconstant convex optimization problem, differentiable problem. And if A is a full column rank, then it can be easily solved, right? So if, and sometimes what happens if the number of equations is much larger than the number of variables in Ax equal to B, it might not just have a solution. Then people seek an approximate solution. And then you just find a minimizer, a point which minimizes the distance between Ax and B. So minimize norm Ax minus B whole square. So that is called the Lasso problem. And some people are nowadays working on problems where they don't put the square here. That is what the Cambridge group is doing in CS, and trying to reduce the gap for that class of functions between what mathematicians look at and what computer scientists look at. There can be, okay, I said, okay, I minimize norm Ax minus B whole square, because least square problems is another way of solving Ax equal to B, subject to the fact that the L1 norm is less than equal to some value R. So there has to be sparsity. Sparse means most of the components now become 0. So if you keep R small, which means there has to be several components which are 0. There is another formulation, which is called the bi-level programming formulation. That is, this is a formulation which has been done by my group here. So it's that you minimize the norm function, the L1 norm function, subject to the fact that X is actually a minimizer of the least square problem. And interestingly enough, we know that this is non-smooth, but this non-smoothness of this will not affect the solution of the problem. So we'll show what we did in that direction, right? But I hope I'll have time because that is too much of a discussion. So any difficulties till now? So there are in the literature, there is essentially the first type of approach, which is slightly difficult. The lasso approach is very common. The second approach that you see here in this is done bi-level programming formulation. This is a very new approach, means that's what my group has done. So let us see what I do not know what would be the outcome finally. Mm. So I, if there is any question at this moment, please. The slides have gone. Hello.
Hi. Yeah, so my
Uh,
internet connectivity got
so yeah,
am I audible? Yeah, I'm audible. My internet got
yeah,
Professor Datta, I have a question if you don't mind.
absolutely.
So Akshay, can you show that slide where both the lasso and the other form are shown?
I mean, before,
Before
yeah,
this.
this one.
Right. So it's more of a comment slash observation. So I had come across lasso a long time ago when I was looking into sparse bases.
Hmm.
There, what they had done is they had transposed the optimization problem into this form because this is convex, right? Like this is provably convex.
Lasso.
Yeah, this formulation.
No, all the problems here are convex.
Right. So there was a paper I came across, and in fact, one of the students when I was a postdoc, he was using this. He transformed the optimization problem into
Mm-hmm.
or a given basis search problem into this, and he was able
Hmm.
to extract a local dictionary, like not a local dictionary, like a dictionary of bases that could
Hmm.
uh, which could be combined in a discontinuous manner, or what do you call it? It's not like a POD basis. It's a basis that you can select only a few components, and then
That's sparsity.
sparsity. Yes. So he was using it in this context. So I'm actually very excited to see this again after a long time. So
Okay, great.
yeah.
Okay, actually, the whole problem is that when we did with this formulation, we really has a solution. Hmm. Then with our formulation, we are getting very fast sparse solutions.
So
But
that is one of the things I remember. So when when you said the speed, when you said that computational effort, extracting the sparse basis was a significant overhead in the computations. Once in
huh,
reduced or sorry, go ahead. So
yeah, no. Actually, sparse. Actually, what this sparse people, why in data sciences this sparse business is important because there's a issue of storage.
correct.
So because you have huge vector, say some 1 million data points, and your decision variables 1 million decision variables. So everything, if it has zero, so you can throw away so many decision variables.
Hmm.
So you store only those which are non-zero. So that makes a lot of sense.
So
So
he was
that is why
applying.
sparsity is very important.
Yeah, so the student was applying it to a very large LES domain, which is a CFD computation
Huh.
domain. So, so this was a major problem, extracting the sparse basis. So, uh, when you said this provides a speed up, so I'm curious to see how in practice it will apply. In the sense, I'm like a user basically to all these concepts.
You know, Vijit, to tell you a story. The mathematicians are very clever people. We'll do this theoretical stuff and do some little computations and leave all these difficult things to computer scientists, to you guys, engineers, and
I
to
know.
do the more difficult stuff. And then we'll say, oh, you see, this is the idea, is ours, and kind of sort of stuff. But I have a huge respect for people doing optimization with engineering because I have a lot of work with Professor Kalyan Mohadev. I'm sure many of you must know his name for evolutionary computation.
Yeah,
Uh,
I teach optimization here at IITB, and I
okay.
use his book. I've looked at Rosinski's book, the one you mentioned. In
Hmm.
fact, I'll get the slides from you. There are some very nice points I can use in my class if that's okay with you.
Sure. I'll just correct the slides. This is a slide in progress. I mean,
No,
I'm
sure.
actually going
No,
to
no
finally
urgency,
form a
but
course with this. Yeah, I like this.
I,
I'll send you the slides, Ravi. No problem.
yeah.
No, absolutely.
I like the way you're explaining the problem because I can actually see myself, I can see a lot of my students connecting with this kind of explanations because they are
Okay.
engineers. They like mathematics, so they come to optimization. But then
Oh,
they become
I I learned so much from Kollan Dev, and we had a lot of exchange because he learned some math techniques, math optimization, and he used it in his paper, and I learned. We have some. I have two papers with him in Journal of Global Optimization, very big papers discussing these kind of issues of this kind of link between the actual math optimization and using the evolutionary techniques. So this is exciting actually.
Yeah,
So
yeah,
next
it
slide,
is.
Akshay.
It is. Yeah. Okay. So I will allow you to continue, but yeah, I would love
Absolutely,
to pick your
absolutely.
brain at some
Stop me
point.
any point.
Yeah.
I have no issue. Now, look at the structure of this problem. So mathematicians have only one goal in life. Jaldi se generalize the problem as soon as possible and publish the next paper before anybody else does. Uh, so the whole idea is to generalize. So mathematicians will observe that, okay, there are the situation here is that here in the Lasso problem, you are minimizing the sum of two convex functions, of which one is differentiable, which is this part, and another which is non-differentiable, which is this part. It need not be not differentiable everywhere, right? So this part, now the question is, it's actually a problem of the form f plus g. I want to minimize such a problem, f differentiable, g non-differentiable. How will I do it? A very good paper in this direction, I think the most important paper in one of the most important 21st century papers on optimization is the shrinkage, a fast shrinkage threshold in algorithms, which is essentially called the proximal point algorithm for linear inverse problem. Actually, they did this, they applied their idea things to some image processing issues. They were trying to de-blur images of that. There's this famous cameraman image. In all image processing papers, you will see some guy holding a camera and they will de-blur it and again try to get it back. So that they did, they published in the Siam Journal of Imaging Sciences, and so they had this name. But there's a huge, beautiful mathematics there, and trying to show the convergence as well as the complexity. So this is a very, very important paper, and I advise any students, especially in electrical engineering, mechanical, aerospace, whoever is applying optimization and needs this kind of handling of large data, or people in image processing, should read this paper at least once in their lives fully, end to end. It is one of the most highest cited papers in this particular area, right? So next slide, Akshay. So you see, as a mathematician, immediately we get into this business of generalizing. So Rn2R function f is differentiable and convex. Rn2R g is convex but need not be differentiable. I need not specify its structure. If g is differentiable, for example, it was lambda norm x square norm, then that is called the Tikhonov regularization. So after the famous Russian guy, A.N. Tikhonov. So the class of methods by which they are solved is called the proximal gradient method. It looks almost like the projection method, but it is much more easier because projection, all for the projection you need the structure of C to be simple. Here there is no C business, it's just Rn. So in the next slide I will just explain what is this. Let's go to the next slide. Look at the gradient method. Nobody would realize, but sometimes people realize it, and this realization was done by back calculation. Please, they did something else and then they got it to it. This is the basic gradient method, the gradient descent method. Then this whole thing, what you see here, can be expressed like this. You might be thinking I am not, I am trying to fool you, but if you calculate the minimizer of this function to this, because this xk is fixed, now you're minimizing with respect to x, so this part is a linear part, this is fixed, so you don't bother. and this part is the strongly convex part. So you add two functions, one is convex, another is strongly convex. You get a strongly convex function, and you get just one minimizer when you minimize it over Rn. So if you minimize it, this is exactly the minimizer. So it is not a, please keep this observation in mind, because on this observation, a whole family of algorithms called the proximal algorithms or of convex optimization is built, and whole of image processing, a lot in data science and machine learning uses the proximal algorithms. So these are very important class of algorithms. So gradient method is actually, this was even known to Cauchy, the gradient method, not this actually, but this structure was known to Cauchy even. So it's a very old method, and this is the foundations. So let's go to the next one. So now if I take the special form of G, instead of F, I have F plus lambda norm x1. What do I do? How do I get the iterative scheme? I am not minimizing with respect to xk, of course, I'm keeping it fixed. Basically, what I have done, I've linearized the function value f around xk and added a quadratic term to it. It's a kind of a quadratic approximation of f around xk. I first take the linear term, and instead of the second order derivative, because I don't know whether the Hessian etc. exists, I just add this term. So get a quadratic approximation of f around xk and add it to lambda x1, and then I minimize this. And if you do it, you can actually make it a little shortcut, calculating out this and writing it in this way, and then you get, then the argmin is written formally as this is written by people in image processing. This is called the shrinkage threshold factor. And in the next slide, this will be explained. If you actually solve this, what you will get. Akshay, the next slide, please. If you solve this, so this T mu that you saw, the T mu thing, it is called a shrinkage operator or soft thresholding operator. So that has a form like this for every component of that, because it's mapping from Rn to Rn. For every component of that, this is the structure, which means this. It actually has a very simple structure. When you solve it, it is very simple. I do not have the time for you, but if it's very sad, Ovijit or Akshay, I don't get a chance to teach them in my classes. I would love to teach them and tell the details. They are so fascinating, actually. So
I'm sure we can invite you for some class lectures.
Oh, okay. I'd love to go to IIT Kharagpur, you know. So, okay. So this is, this is a very simple structure. This is what is used in image processing. Now let's go and see how to generalize it for any function, which could be any G. The next slide. Now, what is interesting is that look at F. When mathematicians have a differentiable function, they have put that in their head that they have to take gradient of F to be Lipschitz, satisfying the Lipschitz gradient criteria. That is absolutely happening if you are taking a function like this, in which the Lipschitz constant is of this form, that twice of the maximum eigenvalue of A transpose A. That's beautiful, of course, but this is what it is. Actually, in my work with my student, one of my former students, in that bi-level problem, we actually throw away this Lipschitz gradient condition, that I don't require your Lipschitz gradient condition. Who's going to check whether it's Lipschitz gradient or not? Just without that, keep on doing it. Okay. So maybe that lecture I have to give it for a separate time. So let's look at this. If you have a Lipschitz gradient condition, this condition automatically holds. It doesn't matter whether the function f is convex or not. It comes out of simple integration, mean value theorem of integral calculus. So, but we will not do it. in fact, if you have convexity, you can just apply the definition of convexity to get this condition, but not with the 2, just LF. So obviously that would be anyway true, because if you multiply just LF instead of half LF here, that would be greater. But just by applying the definition of convexity, that will come. But this more stronger condition comes by applying the integral calculus, which is slightly surprising to me, but it's interesting. The next slide. So now you see that this is the general model of the proximal gradient problem, that I have to minimize a function f plus g. F is convex and differentiable, g is convex and non-smooth, but most people, I would like to say, I want to take g to be even a function like indicator function of a convex set. Indicator function of a convex set is like a penalty term, which gives you the value 0 if x is in that set. It gives you the value plus infinity when x is outside the set. It's not the usual indicator function of set theory. It's an indicator function of convex analysis, which says that I'll penalize you nothing if you are in the set. I'll penalize you infinitely if you are outside the set. So those kind of functions are extended valued functions, but lower semi-continuous. So that kind of extension has also been made. But however, in most structures, we don't need this, right? So we need not bother much about it. I also like to look at things which are simpler, much easy to handle. So as I told you, if whenever differentiability comes, this Lipschitz gradient condition is a kind of baggage that you have to carry in most known algorithms. But that is one of my goals, is to get out of the Lipschitz gradient condition. Can I forget about it and still get similar results? What should be the condition which will give it? So the next slide. What you will depend on the proximal gradient algorithm is the proximal operator. So without knowing the proximal operator is it's not possible to actually understand the idea of the proximal gradient algorithm. What they actually want to do, that instead once given x is x a point, they say an iterate, what they want to do is with a different variable u, instead of solving minimizing fx, right, or they want to fix this reference point x, and around it build a strongly convex function fu plus half of this. So this is the strongly convex part, so for which there will be a unique minimizer. There will be a minimizer surely, and there will be a unique minimizer. Then they want to, if you change the x, the minimizer will change. Right? Now, what you do, instead of solving a convex function, you solve a sequence of strongly convex functions. Strongly convex functions are easiest to solve. It is guaranteed they have a unique minimizer. So that makes much more sense. So this is this operator is called a proximal operator. Actually, if you do not have f to be convex, this is a set actually. For every x, this is a set. It becomes a set valued mapping. But because you have convexity here, f is convex, this is unique. This arg-mean, there's only one element in the arg-mean set, the minimizer set. And so for every x, there's a one value. So it is a function. So it's called that is why it's called the proximal operator, proximal map, or the proximal function, whichever you want.
Professor Datta, is it constructing a ball? Constructing a ball around fu. Like you want to minimize u that minimizes this, but the one half.
No, it's not constructing. It's constructing a ball in what sense? It's constructing. You want fu to be inside some ball.
Yeah. So the fu plus 1/2 u minus x norm is a ball around fu, right?
Is a ball around fu, right?
So you're minimizing.
So I just minute fu plus this. What should be the radius of that ball? It depends on the radius of u minus x, that difference.
Correct.
So so not a single ball. With every u, you are making many balls then.
Yes. So you're I'm still trying to
okay.
figure it
That's
out.
okay. That's yeah. That might be. You might look at it geometrically. Thank you. But I usually look at it in a very simple way, that I have a convex function which can have multiple minimizers. So I want to solve it in a sequence.
Okay.
So at every iterate, I construct a strongly convex approximation of that and solve that problem, because
Okay.
I can show that at the end, these sequences will finally hit the minimizer. That's the idea.
Okay.
So now if you have prox of lambda f, instead of f, if you have lambda, put lambda here, then you can actually show that this argument of this function gives you that prox lambda f x would be here. Sorry. Now why this prox operator is important in the next slide. Why this game is been played? In the next slide we discuss that. Actually, suppose you have this condition that x is equal to prox of x minus lambda grad f x. It's a kind of fixed point type of thing. So if you have this condition, then you can show that x is a solution of the original problem f plus g. So prox of lambda g, and this is your x value. The prox f of x, this is your x value. So then you can actually apply the standard optimality condition and prove that 0 is, if x is the minimizer, if this happens, that is x is the minimizer of that lambda g plus 1 by 2 lambda norm of u minus this term whole square. Then if you take the derivative or subdifferentiate, you take the subdifferential and write the optimality condition, then this is exactly, you will get back this, which means immediately that because convex conditions are both necessary and sufficient, you will immediately have f plus g is minimized at x. So that is why, because of this condition. So suppose x, I take x naught and start, or x1 and start, and x1 is not equal to this, which means x1 is not a solution. So this projection point now becomes a new point. So I write, because it's not equal to x1, so it is, I write it x2 is equal to projection of prox of lambda g x1 minus lambda 1 grad of fx1. So that immediately creates the iteration scheme. So that is exactly what we will show in the next slide. Next slide, action. Yeah. So you see what we did with that lambda stuff of thing, f of f plus lambda x1. We just added the lambda x thing here. So exactly, we wrote a quadratic approximation of f. But in this case, because we know about the Lipschitz constant, we will use the Lipschitz constant also to as a part of the quadratic approximation of f around xk. And then we add it with gx, and this is what it has. And this is exactly equal to the writing xk plus 1 is the prox operator at xk of 1 by lfg, which is this one, argument of this, right? So not xk, sorry, I'm mistaking it. Prox of xk minus this, xk minus this. So there's a error here. This is not this. This is prox of 1 by lfg of this. So it shouldn't be xk, it should be xk minus 1 by lf grad of xk. So this is the point. This is the reference point at which you're computing the prox. So this is the u here actually. X is now become the u. Xk is taking the role of x in the actual definition. So the algorithm is simply just start with x naught and keep on applying the prox operator, and then you'll actually go to the solution. So basically, you are solving. If you just write a sub problem, a sub routine solving, or you can just borrow any routine like CVX from MATLAB to solve that strongly convex problem repeatedly, then in quite fast actually you can go to the solution. So let's go to the next slide. So this, what happened? It got so this is what is called the ESTA, or the proximal gradient algorithm. Iterative soft thresholding algorithm. So it's a name borrowed from the image processing community. So you see, you have the LF, the constant, that Lipschitz constant for grad f. X naught is the initial point, and this is exactly this is you just do that iteration. That's it, nothing else. And of course, you can what should be the stopping criteria. You can design your stopping criteria up to you. It's up to you. It doesn't matter much, but it's up to you to design the stopping criteria. And because you have taken Lipschitz gradient, this is a descent method. The function values actually go down. Okay, so let's go to the next slide. So what did Beck-and-Table showed? Beck-and-Table showed this very important result. He showed that if x star is the solution of that problem f plus g, and xk be the kth iteration generated by the e star, the one, then fxk minus fx star. This is the style we started with Yuri Nesterov, and through that we have this problem, this kind of analysis by mathematicians, the complexity analysis. So fxk minus fx star is less than LF. X naught is a given point, the starting point which you know, and x star is the solution. There is a solution which is assumed. So norm this whole square divided by 2k. So now you will observe as k goes to infinity, because x star is the solution, fxk minus fx star is greater than 0. So anyway, as k goes to infinity, the right hand side actually goes to 0. So basically, because of the sandwich, because this is also should be greater than 0, fxk actually goes to fx star. This is very important. So I don't generate a sequence xk going to x star. I generate a sequence xk so that fxk goes to fx star. So the difference between fxk and fx star is very less. So I can actually choose xk as a quite a acceptable solution. The convergence rate is O of 1 by k, because this structure is nothing but O, capital O of 1 by k, because it's some constant into 1 by k. And to reach an epsilon solution, when I will reach an epsilon solution, if this fxk minus fx star is less than epsilon, then k would be the approximate, xk would be an epsilon solution. So it would be enough if I assume that this part on the right hand side is less than epsilon. So immediately I'll get what? So I'll bring the epsilon this side and take k this side. So it will become some constant into 1 by epsilon is less than k. So to reach that state, that fxk minus fx star is less than epsilon, I must at least take steps, which is the number of steps that I should at least take. The minimum number of steps that I should take is some constant, meaning into 1 by epsilon. So that is the minimum number of steps. If you take more steps anyway, you'll go there. You'll go to the approximate solution. But the minimum number of steps I should take is capital O of 1 by epsilon. Within that steps, I will get to the if this is the least number of steps I take, I go to the approximate solution with the E, with the precision parameter epsilon. Now, Nesterov had an old result for strongly convex functions as how to speed up this steepest descent or gradient descent algorithm, speed it up and make it much faster. The rate would become much faster. It will go to the solution much faster. So how to do that speed up? This is sometimes called the Nesterov momentum generation. So you put some momentum to the iterate. So that we will see in this specialized context, in this generalized context for in this by paper of Beck-and-Table. And then let's go to the next slide. So this is called FISTA, fast ISTA. That is FISTA. So fast iterated soft thresholding algorithm in the same paper. Here it is slightly complex because here you're running two parallel sets of iterates. One is yk, one is xk. So yk is essentially giving you the momentum. There is, of course, let us not try to explain in terms of classical mechanics. It will be a failure. Nobody understands why. it was, I have also spoken to Nesterov. Okay, it happened. This is an observation, right? That why this has happened. But now based on that format, people are trying to applying to many other algorithms. Let me tell you that this has become a big business. This acceleration algorithms. It's a big market now. It's the industry which is happening. You open Siam Journal of Optimization or math programming, there'll be at least one paper which is doing this game. So okay, so this game will continue for some time, but it's fine. So the same story. Now you start with x naught as the initial point and set y1 equal to x naught. So there is another sequence which starts from 1 as the starting, y1 as the starting point, x starts with x naught as the starting point. And alpha 1 is a series of numbers that we'll create, which will act as a kind of a momentum, scaling up factor. That we will start with index 1, alpha 1. But the starting solution will always have an index 0. So xk is the prox of 1 by LFG. So what you do, the proximal step you take with yk. So when you're starting out, you are actually here, this is all x naught. So this will be actually x. This is actually, so x1 is prox of x naught, but that is the first step. That is exactly like the other one is. So that is exactly what you do. I think there is an extra, I have to correct the slides a bit. So xk, now you choose, so yk, so start with y1, so you will get the x1. So basically you have started with x0 here, you will get x1. Now what happened? You already had alpha 1 to start with, which is 1. So you know what will be alpha 2. You do it. And once you do it, now for example, you know x1 and you also know x0, which is y1 actually here. So you know x1, you know x0, and from that you complete y2. Now then go back again and write, you have not got x2, so you have just completed x1. So from x1 to x2 you are going through a different step. You are going through by completing the y's. So this is where the speeding up is occurring. So here you again go back to the first step and write x2 is equal to prox 1 by LFG of the point y2 minus 1 by LF's grad f of y2. This y2 is not x1, by the way. Y2 is different from x1 because it is created out of x1 and x0. So what happens in the previous one, x2 is nothing but prox of x1 minus 1 by LF grad fx1. Here you don't do that. You create a y2 which is constructed out of the last two things, xk, x1 and x0, and that through that you create x2. That increases the speed for some reason. It's still to be very frank with you, okay, when you read the math, it is clear, okay, this is the way you should do it, and but why it would at all do it, I still haven't been able to figure it out. But I'm trying. But figure it out means getting a motivation out of it. I'm sure most people don't. And there's a book called Lectures in Convex Optimization by Nesterov, and I would tell you that reading that book is very, very hard. So I'm trying to extract the idea and make the things simpler, look simpler to people. This extremely hard because the Russians they would write certain things, and there will be so many issues that will come in, and some cases some things will look like errors and people won't be able to understand. There are many points, and I'm trying to write down in my notebooks a simpler version of that, which anybody can understand, even from the engineering field also. So because when I want to talk to about optimization, I also want engineers to understand it's not just a mathematician's game. So this is the structure. So here, what you are doing in Fista, you are coming from x1 to x2, xk to xk plus 1 through one more intermediate step of finding a yk plus 1. You got xk and use xk and xk minus 1 to find yk plus 1, and then use the yk to create the yk plus 1 to create the xk plus 1. And the same story goes on. Okay, the next slide. The next slide is that, look at this thing. In the ISTA one, here it was k. And in the FISTA one, it is k plus 1 square could be written, replaced by k square also. That doesn't mean anything. They should be less than what is in the top divided by 1 by k square, divided by k square. So the convergence rate is O of 1 by k square, and the steps to epsilon optimality is 1 by root epsilon. So you have improved both. So the speed is increased. This O by 1 by, there was a paper by Nesterov, the convex optimization using gradient descent at the rate O by 1 k square in Russian journal, written in Russian in 1983. So this can be generalized even in this situation. So here is, you have got this result. That's a beautiful result, that just by taking one intermediate step, you immediately speed up. It's a quadratic speed now compared to the linear speed in the last one. It goes very fast towards 0, right? So as k becomes larger, it goes towards 0 very fast. So I will not, after this, then comes the story of what I did with my group, but I'll not get into that. That will be too much complex. It'll need more ideas and more stories, and why that has to be done, that has to be done. Let us just finish it at this point, so that people can at least have a feeling that, okay, here is a result where there's a balance being obtained between converging and also going to fast to epsilon approximation. So at the same time, you have this epsilon, the this grad f is Lipschitz condition, which allows you to get a decent direction. So you know what is the output. If you run it up to n times, say capital N times, then xn would be the output that you would require, and so on. So with this, I would like to end my talk here, and I hope this would serve the purpose for this workshop at least. So Akshay, that's it. Anything?
Thank you, Professor Datta, for this. I mean, I do try to venture into mathematics, but of course I waste lots of time just trying to get the language straight, and then comes the theory. But I think the way you explained it, it's nice. I mean, the language barrier is very thin.
Language barrier is thin actually, because I worked with was a Kalyan Dev, and we figured out how to get off from that language barrier. Language barrier is not okay, but the mathematicians use one terminology, you will use another terminology. Like this step size, xk minus lambda k grad fxk. So lambda k is a step size. How much far you move from xk in this direction minus grad fxk, which is the descent direction, so that you get an xk plus 1 where the function value actually goes down. Because you move too far off, venture too far off, you might not get that condition. So that is called in machine learning as learning rate. But that is, this has been called step size for a long time. So the various people having various terminology for the same thing. So it's just like that. So any questions from any
participants, please ask.
Yeah, I am sure participants didn't get much of it.
We have been struggling with the participants to get them to speak. They are very shy.
What is the background of the participants?
Most of them are faculty in engineering colleges. So
then they should speak up, right? That is how you do science. I think these are, I don't know. If you don't speak up in science and engineering, where am I going to speak up?
Yeah. So participant, please, this is last technical lecture. You should
Yeah, there is
speak
no
up.
controversy here.
Yeah.
This is not politics or anything. This is simple science, simple mathematics. You can just ask any question that you want. If you have some, you know, issues, you can obviously debate on that. You can ask questions. That is why I stopped 3 minutes before.
So let me ask one question and then we'll stop. So can you suggest
Yeah.
some book where I can find all this nomenclature at one place, particularly set theory, so which is good for understanding the language, but not so much heavy on content. I would just like to a book which I can read and see that this
Nonlinear Programming by Bazara, Sherali, and Sethi.
Bazara, Shirali, and
This is
Sethi.
Sherali and Shetty. A generation of optimizers, even the greatest ones, now learn their, all of us optimizers have learned their optimization from Bazara Shetty and Sherali and Shetty, and it is so famous that it is now called the Bazara.
Oh, okay.
It's a Wiley book. I think now then there is an Indian edition for the 3rd edition. I have both of them. It's just a wonderful book actually.
Okay.
That's the book which everybody should read, whether you're becoming an optimizer or whether you're an engineer.
Okay.
That book gives you everything in a very clear and concise way. So anything more?
Participants, if you don't have any questions, then we will close the session for the morning and then we'll again meet at 5 p.m. in the evening. Kindly note that this last session will also have an assessment. The assessment will be of 10 to 15 minutes, but we'll start 15 minutes after the session. So it will start at 6:45 p.m. So
Akshay, I'm looking at your condition of your house. This is a house in IIT Kharagpur.
you know how it rains here. So
Yeah, it's a dam. My house is also damp here, right? So I was just seeing your condition there.
But these are old houses. Probably when you were here, these houses were from before that. So these are one of the older ones.
Which one? Which is C-type?
This is C-type, C1 type, yes.
C1 type. Right.
So now we have flats coming up everywhere, but the condition is not good. I mean, जैसे time बीतता है, the housing is new, but the quality is poor, so that everything is at the same level.
Yeah, I have a lot of good friends in IIT Kharagpur. Ravi Brother Mukherjee, possibly would know him as a dean Shrik or something like that.
Okay, so I mean, I'm a young fish here. So the older, bigger fish.
Yeah, we are good friends with PPC and PPD from CSE. So Abhijit, thank you for sending me the invite.
Sure. It was a pleasure. And as I said, I really enjoyed your talk. Can I request you for the slides at some point?
Absolutely.
So that we can share it with whoever's interested.
He has sent it to me already. I'll share it across.
No. He said he wants to edit them also.
Okay.
Sometimes I did a fast typing, so something has missed. So I'll do some editing and send it to both of you. I have both of
that
your
would
address.
be excellent. Thank you. And
I'll
touch bases with you offline, just to.
Okay.
I'd like to continue.
And I'll send you my telephone number also. You know this fellows in IOR, like.
So I know Ashutosh Mahajan and there is Avinash Bharadwaj. Who else?
Yeah, Ashutosh, and also Mallikarjun Rao and Vishnu Narayanan.
So I have heard their names, but I have not interacted with them. I've met Ashutosh though.
Okay. And also I know very well Professor Borkar. So
okay.
So anyway, it's nice to see all of you in the morning.
Yeah.
So bye Akshay and bye Abhijit.
Yeah, bye.
Okay. Bye.
Thanks a lot.
Bye.
Thanks a lot.
Bye. Oh.
Okay, participants, I'll close the session now and we meet again at 5 p.m.
Bye Akshay. I'll catch up with you offline. Okay.
So I'll disconnect now.
Yeah. Okay. Bye.